Alright class, today we're studying section 4.7, the fundamental theorem of algebra. We are going to be able to determine the number of zeros in a polynomial and find all real and imaginary zeros. The fundamental theorem of algebra states that if f of x is a polynomial with degree of n, where n is greater than 0, then f has at least one zero in the complex plane. What this is saying is first we have a polynomial with a degree of 8. For our example, let's say x has a degree of 6. So I could express this polynomial as this, and I could see my three zeros. X would equal -2, and x would also equal plus or minus I. Now this has two zeros in the complex plane, but technically -2 is also a zero in the complex plane because it can be written in the form -2 plus 0i, which would also be in the complex plane. Basically, this theorem is stating that at least one zero, but technically all zeros, can be written as a complex number. The linear factorization theorem states that if f of x is a polynomial of degree n where n is greater than 0, f has precisely n linear factors. Which basically says that you can factor any polynomial to be a linear, to be the product of linear factors, meaning like x plus 3 or x minus 2, or even x plus x plus I or x minus I could be considered linear factors. So let's practice using the linear factorization theorem and the fundamental theorem of algebra. Express as a product of linear factors. So I just want to try to factor this if I can. Factors of 9 add up to give me -6 would be x minus 3 and x minus 3, which we can express as the product of linear factors, x minus 3 squared. Notice, x minus 3 is a linear factor because it's x, which is a linear change. Now what about this one? X squared plus 16. Now technically x squared plus 16 does not factor. And in the past we would get here when we were factoring into stop. But we can express it as the product of linear factors. For example, I could take this x squared plus 16 and solve it. When I square root both sides, I have the square root of -16, which means that I have to pull out an I for the square root of 16. And remember, this is still plus or minus. So x would equal plus or minus 4i. So I could express this as x plus 4i and x minus 4i. And technically that is still the same thing as saying x squared plus 16. It's just really not a way we would normally express it. But notice, now we have x with no power, meaning that we are now the product of linear factors. Let's try another one. Express as the product of linear factors x squared plus 7. So let's think about what numbers multiply to give me 7. I could certainly always solve it. X squared plus 7 equals 0. X squared equals -7, and then square root both sides. So x equals I times the square root of 7. and it's plus or minus I. So I could express this as x plus I times the square root of 7 and x minus I times the square root of 7. And I'll even prove to you that these are equivalent statements. If you FOIL, and then you have minus I times the square root of 7 times I times the square root of 7. So here you multiply the i's together to get negative 1. And then you multiply the square root of 7's together, square root of 7 times the square root of 7 is 7. You still have the minus out front. These cancel. And you have x squared minus 1, negative 1 times 7, or x squared plus 7. So they are equivalent statements. Let's try another one. Express as the product of linear factors. So I'm going to try to factor if I can. Factor out an x, and so I have x squared plus 4. And then again, I can't really factor this further, but if I create a small equation set equal to 0 and solve it, I can create the product of linear factors. Which means that x times x plus 2i and x times x minus 2i would mean that I have the product of linear factors again. Notice, all the x's, no squares, are left. That's what I mean when I say the product of linear factors. You can go ahead and write down this example. We're going to cover this one in class together at the beginning of the class period.